This is lecture 10G on transforming the polar equations for conic sections back into Cartesian coordinates. This is also painful. In order to spare you some of the pain and also to be able to keep your attention to a certain extent during a lecture, a remote lecture like this, I am going to spare you the algebra. Instead, I'm going to point out the crucial steps. When you have this crucial step, a couple crucial steps, you'll be able to see how these problems are done. I think there's one or two of these in the homework. Right. So what we want to do is start with the r theta form of the polar equation and transform it back into the Cartesian xy form. Now, if you remember from the previous slide, we ended up with something like this. We said that the distance from the point to the focus divided by the distance from the focus to the directrix was equal to the eccentricity, and by using some geometry, we were able to write that ratio in terms of the polar coordinates r theta. Then we isolated r. Now, the trick to going back to the Cartesian coordinates is do not isolate r. That just, you're going to have to undo it. What you do is just rearrange this form. So I'm going to rearrange it. I'm going to divide both sides, or multiply both sides by that denominator, and I get the form that looks like this. R equals E, eccentricity times quantity, d minus r times the cosine theta. Now, what is r cosine theta? It is x. X equals r cosine theta. So now I have an expression r equals E times quantity d minus x. So I'm halfway there. I've eliminated one r and one theta and I was able to replace it with x. I still have a problem with r. To get rid of r, we use the Pythagorean theorem. R squared equals x squared plus y squared. Alright, but what in this case I have to square with pen, I have to square this side, right, of the equation if I'm going to square the r over here. So squaring that gives me this form right here. All I did was, I want that to be read. So now I have x squared plus y squared equals e squared times quantity d minus x quantity squared. Alright, now I have no more r's and thetas. I just have this right here. Okay, now I've eliminated the r and theta, so now I'm in Cartesian coordinates. The next step is to rearrange this expression. And what I do now, I hope you see these steps. I hope you see what I did. I used a general expression in polar coordinates, but I didn't isolate the r. Instead, I just rearranged. Then I noted that r cosine theta was x, and I got half of my problem solved. I still have an r on the left-hand side. I replace the r by x squared plus y squared by the Pythagorean theorem. Now I can rearrange. So to rearrange, I take d minus x and FOIL it out. Then I have an x squared term plus a linear term in x, and I complete the square. If this particular conic section is rotated or displaced in some way other than just along the x-axis, then you're going to have to complete the square on x and y. All it is messy. That's all it is. Okay, so now I complete the square, and here's what I get. And I'm going to use this for both the ellipse and the hyperbola. This was just rearranging and completing the square, and I'm sparing you the algebra. Now here I'm going to point out what we do again, not going through all the algebra. Here was the general form at the bottom of the previous slide. All right. Now for an ellipse, I know that the eccentricity is less than 1. So I can sort of use, I know 1 minus e squared is greater than 0. And I can do some manipulation to this general form and rearrange it from here into the form for an ellipse. Once I've done that, I can then identify the a squared, the b squared, and the h in terms of those parameters that came forward from the polar form. That is, in terms of the eccentricity and the distance to the directrix. Here again is that general form from the bottom of 2 slides ago. And now we're going to look at a hyperbola. For a hyperbola, the eccentricity is greater than 1. Right? So I know that 1 minus e squared is less than 0. Right, so I can do all kind of dividing by it and rearranging. here is the general expression for hyperbola. So I take this and rearrange it into this form. Obviously you have to multiply by the reciprocal of the right hand side over here in order to get the right hand side equal to 1, and then do some rearranging, and then you can identify the a squared, the b squared, and the h in terms of the eccentricity and the distance to the origin. For the parabola, the eccentricity is equal to 1. So if you remember in those previous slides, we had terms, denominators with 1 minus e squared or e squared minus 1 in them, and in this case those would be 0, so we cannot start this, we can't start dividing by 1 minus e or 1 minus e squared. So we're just going to start with this general form that we had right up here, right? And this is with a small amount of rearranging. Okay, we can write an equation for the parabola. This is a horizontally oriented parabola. It opens to the left, and now by this rearrangement we can assign, we know that the distance from the vertex to the focus P is equal to the distance from the vertex to the directrix D, which is a defining quality of a parabola. H equals D over 2, that's the horizontal shift of the vertex.